All right, so please, again, don't watch this video until you have tried C, D, and E all by yourself, but we're gonna go over those now together. And I think these are a little easier than the first two, so hopefully you had some success. All right, for C, again, I would kind of stop and ask myself, like, how many things do I need to consider? I need to consider x cubed. I need to consider the function x squared minus 9. And then I really need to consider this entire thing that's the square root of x squared minus 9. And I'm going to think about those last two together. X cubed, that's going to be unrestricted since it's polynomial, so the domain of all reals. X squared minus 9 by itself doesn't have a domain restriction because that's just a polynomial. But the issue is that we now have the square root of something. So the square root of some junk, and the junk is x squared minus 9. All right, so this is the one we have to think about. So again, we cannot take the square root of a negative number and have a real number output. So that means that the junk inside of the square root function, in this case, x squared minus 9, that must be positive. So x squared minus 9 must be greater than 0. So again, I'm going to, instead of just solving that inequality, I'm going to graph this. I know x squared's a parabola. The minus 9 would just translate it down to 9 on the y-axis, the vertex. Well, it translates the entire parabola, but the vertex would be at 9. So I know that these intercepts where x squared minus 9 equals 0, those must occur at -3 and +3. And we can either get there by factoring. So I could either start with like x squared minus 9 equals 0 and factor a difference of squares. Oops, x plus 3. And then I could solve that to get those zeros. Or since it's a simple quadratic, I could say x squared minus 9 equals 0, therefore x squared equals 9. And you just got to remember that has two solutions, that x is equal to positive and -3. Either of those means we can get to our zeros. So again, if x squared minus 9 must be greater than 0, that means I want the part of this graph that is above the x-axis, that is positive. And you know what? I said greater than. I keep catching my mistakes. I can't re-record these videos every time I make a mistake or I'll never be done with the first unit all year. Sorry, x squared minus 9 can be greater than or equal to 0. We can take the square root of 0, it's 0. So we are going to include these negative and positive 3's, that they're good. We can take the square root of 0. All right, so the domain restriction we get from this is that x can be less than or equal to -3, greater than or equal to +3. And again, it helps me to just put this all on a number line. So here's my -3, here's my +3. All right, so we're saying that x can equal -3 or be less than -3, because it's for these values less than -3 that the graph of this is positive. Okay, and then x can be equal to 3, so I'm going to use that closed circle, or greater than 3. For these values of x greater than 3, x squared minus 9 is positive. All right, so our final domain that we could write for part C is that we could go from -infinity to -3, including the -3, or from 3, including the 3, to infinity. So that is the domain for the function h in part C. All right, part D, each time I'm going to look at this and say, like, how many pieces do I need to consider? I've got this natural log piece. I know the argument must be positive. I have x, which itself is a polynomial function, but I would kind of look at this entire fraction as 1 over x. so the stuff in the denominator cannot be 0. We've got a cube root, so an odd index root, and we have a sinusoidal function whose argument we could need to look at separately is a polynomial. A lot to consider, but this problem's not too bad. So with the x plus 2 piece for the natural log, so if we are taking the natural log of x plus 2, that function only exists where the argument x plus 2 is positive. So from that we get that x plus 2 must be greater than 0. It cannot equal 0. The natural log of 0 does not exist. And if you forget, just go back to that graph. That graph has a vertical asymptote as we approach x equals 0. Okay, so if x plus 2 must be greater than 0, subtract that 2 from both sides, and x must be greater than negative 2. So that is the first thing we know about our domain. All right, we said the polynomial x alone doesn't have a domain restriction, but because it's in the denominator, x cannot be 0. All right, the cube root, we said odd index, oops, I don't know why I wrote another 3 there. Odd index roots do not have a domain restriction. So we're looking out for, like, we can't take the square root of a negative number and get a real number from that. So instead we need to, we just need to remember that for odd index roots we can. I can take the cube root of a negative, so there's not an issue. All right, then lastly, the sinusoidal function itself doesn't have a domain restriction, nor does x squared. So I'm just going to out to the side here, write all reals. So the sine of x squared, no domain restriction. I don't think this one's that bad. It's a lot to look at, but I don't think it's that bad. All right, I'm going to make my number line. The only stuff I'm putting on the number line is this negative 2 and this 0. So a negative 2 and a 0. We said that x cannot be equal to negative 2. It must be greater than. So I'm going to put an open circle. X cannot be equal to 0. So another open circle. And then since x must be greater than negative 2, not less than, I'm going to shade in this direction. Skipping over that 0, keep shading. All right, so our domain for the function f in part D, we can start at negative 2, and we could take that up to 0. And then again, parentheses, because we're not including those numbers. And then from 0 to infinity. Last part, not bad at all. I think this one actually these got easier as we went along. All right, e to the x, no domain restriction. That exists on the domain of all real numbers. This part we got to be careful of. 2x minus 1 by itself, the polynomial, no domain restriction, but the square root of something, the square root of some junk, the junk, in this case, 2x minus 1, the junk must be greater than or equal to 0 since it's an even indexed root. So 2x minus 1 must be greater than or equal to 0. So I could just solve that inequality. If 2x minus 1 must be greater than or equal to 0, add 1 to both sides. 2x must be greater than or equal to 1. Divide both sides by 2. Remember, you can multiply or divide an inequality by a positive number and nothing big happens. Like, that's fine. It's when it's a negative we have to be careful because the sign of the inequality flips. All right, so this is our only domain restriction, and that's a perfectly acceptable way of writing it. And we don't really need a number line for this, but just to practice, if I were expressing this on a number line, I would write my 1/2, I'd put my closed dot, I would shade in the positive direction. The number line itself will never be the answer. Like, you've got to tell me the domain. So you could write it like this, or we could just say from 1/2, including 1/2, to infinity. That is our final answer.